Okay, in this section, I've actually combined two sections here. 5.4 is really just the calculus of exponential functions, and 5.5, I'm just going to call that section the other basis. So we'll get to that at the very end. Okay, so one way to give the definition of the natural exponential function is to talk about it from the vantage point that it's the inverse of the log function. So the inverse of this natural log function is actually the exponential function e to the x. And remember, y equals e to the x if and only if x equals the natural log of y. And this function was discussed at the beginning of the chapter, so if you want a review of exponential equations and properties, then see the earlier notes. Okay, so basically the derivative of e to the x is simply e to the x. And the derivative of e to the u, where u is a function of x, is simply e to the u times u prime. Now, I can't remember, I may have talked about this before, but if not, what I am going to do in this section is also talk about integrals as well. So if I've already talked about derivatives of this type, I do apologize, but it doesn't hurt to see it again. Okay, so if you have the function 5e to the x minus 3x squared and you want the derivative, well, the derivative of 5e to the x would be 5 times the derivative of e to the x, which would just be 5e to the x. And then the derivative of 3x squared is just 6x. So the derivative would be 5e to the x minus 6x. Now, suppose instead of that exponent being x, suppose that exponent was going to be e to the x cubed here. Well, then the derivative of 5e to the x cubed, we would have to use this formula, which employs the chain rule. So you would get 5e to the x cubed, so 5e to the u, and then times u prime, so times the derivative of x cubed, which would be 3x squared. And then the derivative of the minus 3x squared, of course, is still minus 6x. But anyway, you can multiply the 3x squared times 5 and get 15x squared. So you get 15x squared e to the x cubed minus 6x. This right here, I don't want to spend a lot of time on this, but this just shows you from the inverse. Remember that we found that the derivative of an inverse is 1 over the derivative of the original function evaluated at this function g of x. So in other words, if I said f of x is natural log of x and g of x is e to the x, well, we know they're inverses of one another. So we know that the derivative of f is 1 over x. And we know if we take this function and evaluate it at g to the x, that would give me the derivative evaluated at g to the x would give me 1 over e to the x. So if you go back and look for that formula for the derivative of an inverse, it's 1 over the derivative of the original function evaluated at the function. So that would be 1 over f prime of e to the x, which is f prime of e to the x is actually 1 over e to the x. So it's 1 over 1 over e to the x, which is just e to the x. So there's one way to show that the derivative of e to the x is e to the x. You can also show it using the definition of the derivative. Okay, this one's pretty straightforward. It's really basically just like the first one I showed you up there, so you can read that one and see. This one says y equals e to the x squared. So if we apply the e to the u rule to find the derivative, we would have e to the x squared times the derivative of x squared, and the derivative of x squared is just 2x. So the derivative of e to the x squared would just be 2x times e to the x squared. Now this one here, it's raised to a power. So what I have to first use is use the general power rule. So I'm going to bring the 4 down, the power 4 down, and then remember you reduce the power by 1, but then you have to multiply by the derivative of the inside. So now the derivative of the inside, the derivative of 4x would simply be 4, and the derivative of 3e to the x would be just 3e to the x. So that would be it. Now you could possibly multiply the 4 over here and get 16 plus 12 e to the x, but you know, that's not really necessary in my opinion. And then here's an application of the quotient rule using e to the x. So remember, for the quotient rule, u over v, the derivative would be v, which is x cubed, times the derivative of u, which is e to the x, minus u, which is e to the x, times the derivative of v, and v is x cubed, so its derivative is 3x squared, and then all over v squared, so it'd be x to the 6th. Now, you can simplify this. If you factor out x squared e to the x, then you just get x squared e to the x times x minus 3. And then you can actually simplify it even further by dividing x squared into x to the 6th in the denominator and getting x to the 4th. So your final result would be e to the x times x minus 3 all divided by x to the 4th. Okay, here's another one where you use the power rule. Notice I went ahead and wrote this as a power. That's 10 plus 5 e to the negative 2x to the 1/2. But to differentiate that, I have to use the power rule. So I bring the 1/2 down, and then it's going to be raised to the new power, negative 1/2. And then I have to take the derivative of this. Well, the derivative of this, the derivative of 10 is 0, and the derivative of this would be 5e to the negative 2x times the derivative of negative 2x, which of course is negative 2. And since this is just 0, you're just going to get this term multiplied by this. And so that's where you get the 5 times e to the negative 2x times negative 2. But actually the 2 and the negative 2, the 1/2 over here and the negative 2 will sort of cancel and give you negative 1. And so I'm going to make the 5e to the negative 2x, I'm going to pull it over here to the front. And the negative 1, of course, comes from 1/2 times negative 2, and then the 5e to the negative 2x goes here. Now you could take this a little further and eliminate negative exponents. I didn't do that here, but certainly you know how to do that to eliminate your negative exponents. Okay, one more here. Here we have e to the 1 over x power. So what we've got to do is we've got to think of 1 over x as x to the negative 1. So now this is e to the u. And so to take the derivative of e to the u, remember it would be e to the u, which is e to the x to the negative 1, times the derivative of u, so that would be times the derivative of x to the negative 1. Well, the derivative of x to the negative 1 is minus x to the negative 2. And then so we have e to the x to the negative 1 times minus x to the negative 2. And if you eliminate your negative exponents here, you get minus 1 over x squared times e to the 1 over x power, and that's your final answer for the derivative. Okay, again, it sure feels like I may have already covered this when I talked about exponential functions earlier, but again, let's go ahead and do it again. If you have y equal x squared e to the 5x, and you want to analyze that function, well, first of all, you have to find the derivative. So I used the product rule to get the derivative, and then I factored out the x e to the 5x, and I get 5x plus 2. So that's the first derivative. Well, then I applied the product rule to this, and it took me a bit of time here to do this because I had to say x e to the 5x is the first term, and then multiply that by the derivative of the second factor, which is 5. And then I took the second factor, which is 5x plus 2, and then I multiplied by the derivative of x e to the 5x. Well, the derivative of x e to the 5x, I have to use the product rule. So I get 5x e to the 5x plus e to the 5x. Now all I did here was FOIL this, and I got these 4 terms right here. And then the first term was from here, 5x e to the 5x, and then I combined like terms, and I got these three terms, and then I factored out e to the 5x, and so I got the second derivative, e to the 5x times 25x squared plus 20x plus 2. Now if you want to analyze this, you can easily see from the first derivative that if you set this equal to 0, you get x equals 0, or you get x equal negative 2/5. And I'll leave you to test the intervals, but if you test the intervals, you'll find that the function is increasing from negative infinity to negative 2/5 and 0 to infinity, and it's decreasing on negative 2/5 to 0. Well, by the first derivative test, that means you get a relative max of f of negative 2/5, and then you get a relative minimum of whatever f of 0 is, which of course is 0 in that case. Now, in the second derivative test, you actually have to set this equal to 0, and if you solve it using the quadratic equation, then the quadratic formula, then you get x equals minus 2 plus or minus the square root over 5, which is about negative 0.7 and negative 0.1. And then if you test the intervals for that, you'll see that it's concave up from negative infinity to negative 2 minus square root of 2 over 5, and negative 2 plus square root of 2 over 5 to infinity, and then concave down between those two expressions. And then you'll find that the points of inflections are these points, this negative 2 minus square root of 2 over 5, and of course its functional value, and negative 2 plus square root of 2 over 5 and its functional value. Now I didn't really care about trying to figure out what those y values are, because I didn't want to have to plug these back in using their form, that they're those in their exact form. Well, if you graph it at first, you may not see anything, but if you blow it up, you'll see that we get 2 points of inflection. There's a point of inflection right here. It's concave up, then it goes concave down, and then it goes back concave up again. And you'll see you also see you get a extrema here, and you get another extrema here. So you get a relative max here, and you get a relative min here. And so that's what you get there. And then so you'll notice that the y values of these three numbers are very, very small. So see, that's 0.1 right there. So they're very, very small values. Now here's another example. Then you can freeze the video, and I'll leave you to use calculus to analyze this function. And so you'll need to find the first and second derivative, and then determine from the first derivative the critical numbers and extrema, and then from the second derivative you'll need to determine any points of inflection. And then when you're ready, you can try to graph it using the information you gained here. Hopefully you got the same information I got, and you can see here there's one extreme value here, and it's concave down in here, and then somewhere in here, it looks like at negative 2 from my answer, it switches from concave down to concave up and stays concave up throughout. And so that's all that I'm going to talk about on this video. On the next video, I'll talk about implicit differentiation involving exponential functions.